Thank you. The first thing I want to acknowledge is that my collaborator Chen Wang at University of Utah was really instrumental in driving this work. I was previously at Meta when this project began. Chen won a request for proposals, and we continued it because we were so excited about the potential for this idea. So I don't think I need to tell people in this room how dire the e-waste crisis is. We're generating millions of tons of this a year, and we're not slowing down. There's more rapid tech turnover. That's something that's going to continue to happen. We have the third world becoming increasingly technologized. And we have the increased ubiquity of electronics, the Internet of Things. I can't buy a refrigerator today that isn't smart. And so we're going to keep generating this. And there's now some really interesting geopolitical concerns. When we just toss this into a landfill, not only do we have to worry about what happens to the toxic materials as they degrade, but we can't assume that the global supply chain is intact. We have a lot of geopolitical instability, and we're throwing away precious materials that would be valuable to repurpose for other reasons. So there is a lot of work that's going on here from a material science perspective, and I'm going to apologize. I'm a polymer scientist first, not an electronics person. But one very simple solution framework that you can propose is that you just utilize clever polymer chemistry tricks to dissolve away the electronic substrate, right? And that will allow you to collect and reuse the electrical components if your reprocessing step is mild enough. And there's some examples from literature that I'm going to highlight. First one from NC State, where they had a biodegradable electronic substrate. This was just an agarose hydrogel. And another one from Carmel Majidi's group at Carnegie Mellon. They were using a thermoplastic as a substrate. This work was also noteworthy because they were using an electric ink that was based on liquid metal that they could break that oxide skin and then collect that as well. So they were both repurposing the conductor and dissolving the substrate. But this is academic work, and there's a few gaps here that I want to talk about, and that's that it's really ignoring pragmatic considerations. So first, they're not considering how processable their substrate is in a scalable manufacturing workflow. For example, thermoplastic polyurethane, thermoplastic, the name implies it's going to melt at some point. So you lay your components down, and then you go through a solder reflow step at 250 C. That substrate's liquid. You're going to lose your registration after you heat cycle. You also will struggle to make multi-layered circuits with that in a scalable process. The other thing is, in the case of biodegradation, for example, that's a dangerous game because you have to balance your degradation rate when you want it to dissolve versus the lifespan of the device, right? And so in my opinion, it's better if you can have stimulated degradation and not just something that occurs naturally with biological processes or moisture. And this is something that I'm guilty of, so I'm a hypocrite. But as an example of how these substrate projects fall short is that the circuits you see are really, really simple. It's just like an LED that lights up, and that's enough for an academic paper. But that LED is not a really demanding circuit, right? You're not putting many traces close together. You don't care about the dielectric loss, the dielectric constant, the thermal conductivity. And this is all pointing to the flaw in many of these works is that they're trying to show that they can do this without thinking about what the actual needs from the material are. And so we tried to flip this on its head and say, well, the quintessential flexible electronic substrate is polyimide. So rather than trying to force another substrate to be an electronic substrate that might not meet the higher end material properties, let's start with what we know works and see if we can make that reprocessable. So you're I'm sure well aware that polyimide has a host of properties that are attractive, the mechanical, the thermal, right? It has a really high sealing temperature, really good thermal conductivity, low coefficient of thermal expansion, and importantly, great dielectric properties. These all stem from the conjugated nature of the repeat unit in the polymer. But in order to make polyimide, it's a nasty process. You usually have these dilute solutions of polyamic acid that you have to condense at very, very high temperatures. And it's we can scale that right there. You can buy Kapton commercially in any thickness, essentially. But once you form that polyimide sheet that you buy, it's insoluble and infusible. You can't melt it, you can't dissolve it, which limits processing, but more importantly, it limits reprocessing. And so what did we do? Well, we decided to create the monomers and see if we can make it work. So we made these diallyls imides. I know you might